Well, I hope statically indeterminate systems don't become your Death Star. Remember, Death Star got destroyed, and we'll be able to solve and destroy indeterminate problems too. So go ahead and take a look at another example of how to do that. When we look at statically indeterminate problems for one-dimensional systems, there's basically two types of problems we come across. One was seen in example 1 when we have a rigid bar that is bound or fixed on both sides, and then we have a force applied somewhere between it, and we don't know the distribution of how that force gets distributed to either side of the support reactions. The second example is one like we see here, where we have a bar that's made of two materials. We have, in this case, an aluminum rod that is reinforced with a brass core. We want to determine the average normal stress of the aluminum and the brass for this problem. Why is this one a statically indeterminate problem? Well, if you don't have an immediate answer, let's look at our engineering toolbox. So we always start our problems with equilibrium. So let's go ahead and apply equilibrium to this particular bar. So if I look at the bar and I draw a free body diagram, I see that I apply 8 kips at point B, then my reaction AX should be to the right and is probably going to be 8 kips. And I can prove that with my sum forces in the X equation. So we'll go ahead, sum forces in the X equals AX minus 8 kips equals 0. So I can solve that AX equals 8 kips. All right, so that's good. So I don't see anything that's really statically indeterminate about this particular problem. It seems like I have one equation and one unknown, and I was able to solve. The problem comes from figuring out what is the average stress in the aluminum and the brass. Well, how much of that 8 kips is traveling through the brass core, and how much is traveling through the aluminum shell? If you're stumped on that question, that's because this problem is statically indeterminate. And so we can more clearly see why it's statically indeterminate by taking a free body diagram of a cut as shown. When I draw my free body diagram, I see that at point B I have 8 kips applied. And then where I made my cut, I have internal forces. And again, I'll draw my internal forces, positive in tension, so away from the surface of the cut. And so I have internal forces in both the aluminum and the brass. So how much force is carried by the aluminum and how much force is carried by the brass? Well, it's not easily identifiable just by looking at the problem. So we're really going to need to go through all our calculations in order to figure out what the average stress is in the aluminum and the brass. One thing that is pretty easy to determine, though, is that from sum forces in the X, I can identify that P aluminum plus P brass has to equal the 8 kips of compression force that is applied. So you see there my sum forces in the X equation, and ultimately I get my first kind of equation from equilibrium that together the aluminum and the brass have to total 8 kips compression. But I don't necessarily know how much one is taking versus the other. And so I'm going to keep on using my engineering toolbox to figure out what that relationship is. Our second tool in our engineering toolbox is kinematics. So in kinematics, we relate displacements to one another. So when I apply 8 kips of compression at point B, I will generate a displacement in the rod towards point A. I think we can all see that this cylindrical rod, AB, will compress as such. And again, I'll shade in kind of my final deflected shape. And I've drawn here the deflection at B, delta B, is how much this rod compresses. Now in kinematics, I'm relating displacements. So more specifically here, I need to come up with a relationship between the displacement in the brass and the displacement in the aluminum. Because the brass and aluminum are perfectly bonded together, we will assume that they must deflect the same amount, and that amount is the same as delta B. So we can write our kinematics equation as delta B equals delta brass equals delta aluminum. The final tool in our engineering toolbox is material law. And in material law, we relate forces to displacements. So we said that our material law for both aluminum and brass, which will be ductile metals, in the linear elastic range follows Hooke's law, which is PL over EA for that particular segment. So I'll take this delta equals PL over EA, and now I just want to apply it to both the brass and the aluminum. So I can write an expression for delta brass as P in the brass times L of the brass divided by E of the brass, A of the brass. And likewise, I do the same for aluminum. Delta aluminum equals PL over EA, all pertaining to the aluminum shell for this cylindrical rod. Once more, I'll give these equations numbers. You can see I have equations 1 and 2 numbered already. These last two equations will become equations 3 and equations 4. All right, once we get through these three stages, all that we have left to do is to do the math, substitute 1, 2, and 3 into each other in any order and kind of solve the puzzle to get to how much force is in the aluminum and how much force is in the brass. So I will substitute 3 and 4 back into 2, which 2 basically said that the deflection of the brass core has to equal the deflection of the outer aluminum shell. So substituting 3 and 4 into that relationship, I get PL over EA of the brass core equals PL over EA of the aluminum shell. And this will allow me to establish a relationship between P brass and P aluminum. Okay, and so all we're doing is creating kind of like two ratios, and how am I going to figure out how much P brass is relative to P aluminum? Well, all has to depend on the lengths, the modulus of elasticity, and the areas of each of the members. And those three things, the length, the modulus of elasticity, and the area, will determine what proportion the brass and the aluminum will share the applied load. So up here, I'm just going to denote out, here's the brass core and the aluminum shell. The reason I wanted to bring you back up to the problem statement is just we have to note that the aluminum shell is the outer portion of this circle. So when we do the calculations for the aluminum shell, we'll have to subtract out the area for the brass core. All right, so working through our calculations, we have P brass times the length of the brass, which here is 15 inches. That's the total length of the member, divided by the modulus of elasticity for the brass, which is 14,600 KSI, and then also divided by the area, pi over 4 times 0.5 inches squared. We set this equal to the values for the aluminum shell. So we have P aluminum times the length of the aluminum. Again, because these two, the aluminum and the brass, happen to be the same length, this will not really factor into this equation or this relationship. And then we finish out the modulus of elasticity and the area for the aluminum. I'll just make a note here with the area on the aluminum. Make sure again that we're taking the total, I'm taking the total circle, and then I'm subtracting out the brass core to get my area for the aluminum shell only. This is just a geometrical area, so just make sure you don't overlook that step. Doing the math, I get that P brass equals 0.4591 times P aluminum. And so this now gives me another relationship between P brass and P aluminum. And then I can use this in combination with equation 1, where I have a relationship that involves P aluminum and P brass, and ultimately I'll be able to solve for how much force is in both the aluminum shell and the brass core. From equation 1, we get that P brass plus P aluminum has to equal -8 kips. So plugging in my result from equation 5, I get 0.4591 P aluminum plus P aluminum equals -8 kips. So that means 1.4591 P aluminum equals negative 8 kips. So I can solve for P aluminum. I get that P aluminum is negative 5.483 kips, the negative sign indicating that the aluminum shell is in compression. And then using the relationship 0.4591 times P aluminum, I can solve for P brass. P brass is negative 2.517 kips, also in compression. Now that we have successfully found how much force is in the aluminum and the brass, we can get back to what the question was originally asking us. It originally asked for us to determine the average normal stress in the aluminum and the brass. I just want to note that this particular problem didn't just come out, didn't scream, I'm an indeterminate problem, make sure you use your engineering toolbox. So we have to learn through practice and being able to identify the statically indeterminate nature of these problems so that we know when we have to use our engineering toolbox and solve a statically indeterminate problem versus other cases where it'll be statically determinate. Our final step in the problem is then to solve the average normal stress. The average normal stress, as you recall, is sigma equals P over A. So I need to do this for both the aluminum shell and the brass core. So sigma aluminum equals P aluminum over A aluminum. For the brass, sigma brass equals P in the brass core divided by the area of the brass core. And so now I'll just plug in my numbers I have for the axial force in the aluminum. I have that this is negative 5.483 kips. Then I have to use the area for my aluminum shell. Again, remember that when calculating the area for the aluminum shell, you have to take the area of the outside circle and then subtract out the area for that inner brass core, that inner circle. And so we did this calculation above, and then I'm just repeating it here for the area. Likewise for sigma brass, I know that the axial force in my brass was negative 2.517 kips. And I divide that by the area of the brass core. And so if I sharpen my pencil and type my numbers in my calculator, I end up getting that sigma aluminum is equal to negative 9.31 KSI, which is the negative sign again indicates compression. And sigma brass is negative 12.82 KSI, also in compression. I hope you found this problem pretty straightforward. It's another good example of when we need to apply our engineering toolbox to solve a statically indeterminate system. It's a little bit more straightforward than example 1, since I think it's very easy to see the kinematics condition that the deflection in the brass core had to be the same as the deflection in the aluminum shell. So I think that's a little bit more visually easy to see. But nonetheless, the solution steps were the same, and we were able to solve for the stress in both materials. Now we get to look forward to learning the force method. Indeterminate systems solve correctly you can do. Now it's time to awaken the force inside you.